Speed of sound waves. We live in a world of sound. Anywhere we go and whatever we do, we hear sounds. Sound is restricted to the frequency range of 20 Hz to 20,000 Hz, to which human ear is sensitive. Waves with frequency below this audible range is called infrasounds, and those above are referred to as ultrasounds. Sound wave is a pressure disturbance that travels through a medium by means of particle-to-particle interaction. Like any waves, the speed of sound waves refers to how fast the disturbance is passed from particle to particle. Sound waves are longitudinal waves. They are produced by a series of parallel directions of travel of the waves. Example, when you pluck a strings of a guitar, the string will look hazy as they vibrate. When you ring a bell, you pull the strings and move it back and forth to produce sounds. Speed of sound is not as fast as light. Noise can also be propagated by metal, wood, or water. The speed of sound is dependent on the carrier material. The more rigid the material is, the higher is the speed. Sound waves exist as variation of pressure in medium such air. It is created by vibration. The vibrating air then causes the human eardrum to vibrate, which brain interprets as sounds. Sound waves can also be shown in standard X and Y graph. The wave shown represents a constant tone at a set frequency. Propagation of sound waves. Like water waves, sound waves need a medium to spread in. Sound waves can travel in air, water, and solids. Consider a vibrating tuning fork. As the prongs of the fork move back and forth, they disturb the air molecules close to them, creating a back and forth movement of the air parallel to the direction of waves. These air molecules likewise transfer their motion to the neighboring particles and to the other molecules. The air molecules then strike your eardrum, making it vibrate. Nearly all sounds reach you with air as the transmitting medium. Dense gases are better transmitters of sounds than rare gases. As you climb mountains, you must speak little louder to be heard. Air in the mountain is less dense in the lowlands. It does not transmit sound so readily. Just like the light, the speed of sound can be calculated using basic wave equation. When you're going to find the speed of sound, multiply the wavelength and the frequency. When we do the manipulation of formula, we're going to find wavelength. Wavelength is equals to speed of sound over frequency, and frequency is equals to speed of sound over wavelength. Wave is the distance between two corresponding points on a wave train. Frequency refers to the number of waves passing at a given point at a given time. The results of a number of experiments shows that the speed of sound in air at 0 degrees Celsius is approximately 331 meters per second. For each degree rise in temperature above 0 degrees Celsius, the speed increased by 0.6 meters per second. Thus, at any temperature in degrees Celsius, the speed of sound in air in 0 degrees Celsius is determined by the equation speed of sound is equal to 331 meters per second plus 0.6 meters per second multiplied by the given temperature. For example, what is the speed of sound in air at 30 degrees Celsius? Using the equation, speed of sound is equal to 331 meters per second plus 0.6 meters per second multiplied by the given temperature. When we do the equation, speed of sound is equal to 331 meters per second plus 0.6 meters per second multiplied by 30 degrees Celsius. First, we're going to multiply 0.6 meters per second by the given temperature, which is 30 degrees Celsius. Then add it with the 331 meters per second. The speed of sound is equal to 349 meters per second. As mentioned earlier, the speed of any wave depends upon the properties of a medium through which wave is traveling. The elasticity and the density of a medium affects the sound propagation, wherein the elasticity is the property of matter that enables it to retain its original size and shape when external force is removed. Thus, the speed of sound differs in media. Higher temperatures also increase the speed of sounds. For solids and liquids, the change in speed is small and can usually be neglected. For gases, the change is large. The speed increases with temperature.
Standing waves in pipes. Everybody was created a stationary resonant harmonic sound wave by whistling or by blowing over a beer bottle, or by swinging a garden hose, or by playing the organ. In this section, we will see how to compute the harmonics of a given pipe geometry of an imaginary organ pipe that is open or closed at one or both ends. Closed-ended pipes. Remember that it is actually air that is doing the vibrating as a wave here. The air at the closed end of the pipe must be anode or not moving, since the air is not free to move there and must be able to reflect it back. The simplest smallest wave that we can possibly fit in a closed-end pipe is shown in this figure. Notice, even though it has been flipped left to right and it looks squeezed and stretched a bit to fit, it is still 1/4 of wavelength. Since this is the smallest stable piece of a wave we can fit in this pipe, this is the fundamental or first harmonic. Since the length of the tube is the same as the length of 1/4 wavelength, we know that the length of this tube is 1/4 of a wavelength. This leads to our first formula, which is length is equals to 1/4 multiplied by wavelength. We have to solve this formula for wavelength, then combine it with the formula of speed is equals to frequency multiplied by wavelength to get a more useful formula. Length is equals to 1/4 multiplied by wavelength. Wavelength is equals to 4 multiplied by length. Speed is equals to frequency multiplied by wavelength. Speed is equals to frequency multiplied by 4 times length. Frequency is equals to speed divided by 4 times length. When the wave reaches close end, it's going to be reflected as an inverted wave. Going from the air to whatever the pipe is made of is a pretty big change, so this is what we would expect. This would look like this figure. What does the next harmonic looks like? It's the third harmonic. I know this name might be a little confusing, but because of the actual note produced and the way the waves fit in, musicians refer to the next step in a closed-end pipes instrument such as third harmonic. There is no such thing as second harmonic for closed-end pipes. Remember that we have to have an antinode at the opening where the air is moving and a node at the closed end where the air can't move. That means for the third harmonic, we can get something like this figure. This is 3/4 of wavelength fit into the tube, so the length of the tube is length is equal to 3/4 multiplied by wavelength. This is the third harmonic of the closed-end pipe. The formula for the frequency of the note we will hear is frequency is equal to 3 multiplied by speed divided by 4. Do you notice a pattern forming in the formula? Hopefully, because for both open and closed-end pipes, we will only give you the formulas for the fundamental length. You need to remember how to get the rest. If we drew in the reflection of the third harmonic, it would look like this figure. One more to make sure see the pattern, the fifth harmonic. In this figure, there is one full wavelength in there, 4/4 plus an extra 1/4 of the wavelength for a total of 5/4. The length of the pipe is length is equals to 5/4 multiplied by wavelength. And the note produced by fifth harmonic is found using this formula. Frequency is equals to 5 multiplied by speed divided by 4 times length. This figure shows the reflection of a fifth harmonic for closed-end pipe. For the open-end pipes, the fundamental or first harmonic for an open-end pipe needs to be an antinode at both ends, since the air can move at both ends. That's why the smallest wave we can fit in is shown in this figure. That means the length of the tube and frequency formula are length is equals to 1/2 multiplied by wavelength, and frequency is equals to speed divided by 2 times length. The whole thing after it reflects at the other end looks like this figure. The next note we can play is the second harmonic. Open-end pipes have second harmonic. They can have any number harmonic they want, odd or even. Again, it looks weird, but trace it out and you'll see that there is exactly one wavelength here. The length and frequency formulas are length is equals to 2/2 multiplied by wavelength, and frequency is equals to 2 multiplied by speed divided by 2 times length.